Welcome to today's central exercise session in Mathematics 2. As usual, we'll be ready to answer your questions in chat, so please use chat.tum.de to ask your questions. And we're waiting for your questions on this channel here, MA9714-CE. As usual, the chat is moderated by Alind Carlson. We'll be discussing sheet number 11 today. So here's sheet 11. Main topics of that sheet are integration using the change of variables formula. And in particular, we'll discuss integration using polar coordinates as an example for that. And then we'll discuss curves. So C11.2 and 11.3 are about curves in 2D and 3D space. So let's start with the integration problem. So here's C11.1. In 11.1, the task is to compute an integral, specifically this one here, integral over 1 over x1 squared plus x2 squared dx1 x2. And the domain of integration is D, which is defined like this. So we have x1 squared plus x2 squared is less or equal to 9 and greater or equal to 1. Okay, so this set D here that we're considering for our integration, you can probably tell how this looks already. But let's spend a few minutes talking about that. So as you can see, this expression here in the middle, that is exactly equal to the norm of x squared. So that's the distance of a vector x from the origin squared. So what this set D is geometrically is a set of all vectors such that their squared distance to the origin is at least 1 and at most 9. Or in other words, their distance to the origin is between 1 and 3. Geometrically, that means we have a set that looks like a ring. So we have an inner circle with a radius of 1. And an outer circle with a radius of 3. And that set D is the set of all points that are in that ring here. Right, so that's D. And as you can probably imagine, it's not that easy to describe D in terms of Cartesian coordinates. It would, of course, be possible. But it's much easier to describe this in terms of polar coordinates. And that's why we want to use polar coordinates for this integration task here. So what we need first is a representation of D in terms of polar coordinates. So we want to describe the points in that set D in terms of their radius and their angle. And then we want to consider their transformation. So we have T of R and phi, R being the radius, phi being the angle. Now, what radii and what angles do we allow? Obviously, the radii are somewhere between 1 and 3. So all of these are allowed. And the angle, we have everything from 0 to 2 pi. We're doing a whole rotation around the origin here. So the description in polar coordinates would be 1 is less or equal to r is less or equal to 3. And phi is between 0 and 2 pi. So obviously all the boundaries are constant in terms of polar coordinates here. And of course, that should make the integral easy to compute if the expression we integrate over, of course, is sufficiently simple. Okay, so that's a description of D in polar coordinates. And now to compute the integral, we need to use the change of variables formula. You will remember that to compute the integral of a function f of x1, x2, dx1, x2 over d, if we want to do this in terms of polar coordinates, so here we have the transformed version of d, and here we integrate over the polar version. Let's just write down that's the Cartesian version, and here we want the polar version. What we do is, of course, we have to consider f of t of r and phi. Right, so we need to apply the transformation to r and phi first, and then apply f as that is given in Cartesian coordinates. And then we need to multiply this, and we multiply this by the determinant of the Jacobian of our transformation of r and phi, or its absolute value to be more precise. And then we can integrate this dr phi, right? So we change the variables of integration through this transformation here. So what we need to compute is we need to compute this Jacobian here, or more specifically, its determinant. And that means we need to know about this t. So here we're using the transformation from polar to Cartesian coordinates for that. And as you hopefully know, that is given as r cosine of phi and r sine of phi. And now for the determinant of the Jacobian, I'll do the computation here. But of course, you will remember that we did this in the lecture already. So just to be clear, you don't have to repeat this computation in the exam. It does need to be clear where this factor comes from, whatever factor that is. But if that is one of the factors that we have computed in the lecture videos already, then you can just use that, right? Without computing it once again. Okay, so just to see how this would work, to compute the Jacobian, what we do is we compute the partial derivatives of this and this row with respect to r and with respect to phi. So differentiating with respect to r yields cosine of phi in row 1 and sine of phi in row 2. And then differentiating with respect to phi, so the derivative of the cosine is the negative sign. So that means we get minus r sine of phi here. And for the sine, the derivative is the cosine. So we get r times cosine phi here. And then we need to compute the determinant of that. So that's a 2 by 2 matrix. So that's easy to compute. And the result is r cosine squared plus r sine squared. So we get r cosine squared plus sine squared. And as you know, this expression here, that is 1. So the result is simply r. Right, so that is our determinant. And now let's apply this to the function that is given here in this problem 11.1. So that means our integral over that set d here. The function was given as 1 over x1 squared plus x2 squared, and we wanted to integrate that dx1 x2. Now, by the change of variables formula, that's the same thing as integrating over the polar description here of f of r cosine phi and r sine phi times r. Now, remember the radius in this case that is between 1 and 3, so that's positive anyway. We don't need the absolute value. And then we integrate this dr phi. Okay, now for the function, as you can probably see already, what we get here is r squared cosine squared plus r squared sine squared times r dr phi. So this expression here, that's r squared times cosine squared plus sine squared. So again, cosine squared plus sine squared is 1. So we get 1 over r squared times r dr phi. And that leaves us with the function 1 over r to integrate. Basically, the order of integration is up to us now. Let's get this r out of the way first. So let's integrate r from 1 to 3 first, and then phi from 0 to 2 pi dr d phi. Okay, and if you want to do this, well, the integral of 1 over r is the ln, the natural logarithm. So the first integral becomes ln of r. The boundaries are 1 and 3, and we still need to integrate this d phi. So this here becomes ln 3 minus ln 1. ln 1 is 0. So we're left with just ln 3 d phi. And now that becomes phi times ln 3 for phi from 0 to 2 pi. So we get 2 pi times ln 3 minus 0 times ln 3. So that's 2 pi ln 3. And if you get an expression involving functions like the ln or the sine or the cosine or the tangent of something, we don't know the exact value, then just leave it as it is. So that result here is totally fine. Okay, so that's the result of this integral C11.1. Questions?
Yes, so there's quite a few. First of all, why can we simply use the determinant of a Jacobian? I cannot remember there was an explanation about this.
If you watch the videos of that specific lecture about the change of variables from, yeah, you should get the explanation for that. So basically the idea is that the determinant somehow captures, there we are free, the determinant captures the change in volume incurred by this transformation of the coordinate system. And you need to account for that change in volume if you want to compute the integral. So that's basically what this term here does. Yeah, again, there's a video about that. It's called Change of Variables. Watch that one.
Okay, and then there's a question. Why can we integrate over a variable that does not even exist in the term?
Which term are we referring to?
The angle. There is no angle.
Well, it doesn't really matter, right? I mean, we can integrate over anything we want to. The question is, how hard is it to compute the integral? And if the variable doesn't exist in the term, even better, because basically we're integrating a constant. And of course, that's entirely possible. Remember, integration in one dimension. Basically, integration in one dimension means the inverse of differentiation. So if you want to integrate a constant, basically the question you ask is, what function, if I differentiate it, yields a constant? And the answer is basically F-linear function, right? Something times x, if you differentiate that, you will get something, just the constant, the x vanishes. So in reverse, if you integrate over a constant, the result is x times that constant. That's exactly what we do here.
Okay, and then there's one question. So I understand that one doesn't need to provide the proof of how we derive that the Jacobian equals R for R cos X, R sin X. But what about when we are dealing with R3? So cylindrical coordinates instead. Like,
so we have seen examples for polar coordinates in 2D and for spherical coordinates in 3D. So those are the formulas that I know you know. You don't have to derive these anymore. There hasn't been an example about the cylindrical coordinates in the lecture videos, I think, as far as I remember. Feel free to prove me wrong. So I'd say if there is a question, or if you compute an integral involving cylindrical coordinates, of course, you would have to derive the determinant of JT.
So you can use that, you know, polar coordinates, and then it's not.
Yeah, it's not that hard.
Okay, and just, yeah, so I think that's what I see so far. There's someone typing, but yeah, don't see anything.
Okay, so I'd say let's continue with 11.2 then, and we can of course always get back to that problem here again. So C11.2. So this one is about curves, and we're starting by just drawing sketches for a few selected curves in the plane and often in 3D space. So the problem statement is somewhat misleading, as I see. So we start with that one curve here. And a parameterized curve, as it's called, is always given by, of course, a parameter space. We usually think of that parameter as being time, but of course, there are different possibilities. You could also use angle, for example, if you want to talk about polar curves. Those can be parameterized by angle. You could parameterize a curve by its length, for example, or by very different things. Usually, we just think of that as time. So that's the most general interpretation, basically. And then there's a codomain. That's usually R2, R3, or some higher dimensional space. And of course, we need some mapping that tells us how to compute the coordinates of a point from that parameter t. So basically, we say that at a certain time t, the curve produces this point. So you could think of some particle moving in the plane. And at a certain time t, the position of the particle is given by this expression here. So that's basically the idea, the visualization behind parameterized curves. So for the first one, we have this parameter space that is the interval from 0 to 1. The curve lives in the plane in R2. And it's given by gamma 1 of t equals t squared. So how does that look like? So let's draw a plane, x1, x2. And then for t equals 0, for example, the point that we get is simply 0 squared and 0 squared, so the origin. That means the curve starts at the origin. This is t equals 0. At the end of this parameter interval here, 1, we get 1 squared, 1 squared. So that's the point 1, 1. That's where the curve ends. So this is 1, 1. And this corresponds to t equals 1. And then what happens in between? Well, you can easily see that the x1 and the x2 coordinate are always equal. And that means we're basically moving along this line here from the starting point to the end point. So that's what the graph of that function looks like. And of course, that's not the only possibility, not the only possible way to parameterize that, that line here. For example, if you wrote that curve as tt instead of t squared, the look of that graph would be the same. The difference of those two curves is how they move along that line. Right? So they start at the same point, they end at the same point. The path is exactly the same, but the speed the movement along that path, that is different. For this curve here, you can see the speed of that one. Speed is basically given as the derivative. That's 1, 1. So that particle is moving along this 1, 1 at constant speed. Whereas if you differentiate that one here, you will get 2t, 2t. So you can see that starts out very slowly at 0. And then the speed increases as t increases. So that particle accelerates along its way, right? So basically you start off very slowly, like moving here, and then you get faster and faster until you reach the end point. Whereas for this parameterization, you would move at constant speed, right? Like this. But again, the graph, the trace, as you could also say, of that curve is the same. And of course, there are other parameterizations that yield the very same trace. Okay, questions about that one first before we proceed?
I see no questions so far.
Wonderful. And let's take part B. Gamma 2. Now that one has a parameter space of 0 to 2 pi. And if pi is involved, then usually trigonometric functions are involved in that curve, because otherwise it usually doesn't look very nice. And indeed, the parameterization here is gamma 2 of t is given as sine t and cosine of t. And that's also one of the basics I should be aware of. So what happens here is something like this. So the starting point of this curve here, sine t, cosine of t, for t equals 0, we're starting at sine of 0, cosine of 0. So that's 0 and 1. So the starting point of this curve is here, 0 and 1, right? You will hopefully remember that basically this describes movement along a circle. So if you compute the norm of gamma 2 of t, then what you get is the square root of sine squared plus cosine squared. So that's simply 1, right? Every point is on the unit circle. And of course, we're moving along that unit circle, right? The x and y coordinate constantly changes here. The question is, where do we start? Where do we end? And how do we move along that circle? And in this case, what happens is if t increases, then the sine will also increase. Let's have a look at the sine function. So basically, the sine function looks somewhat like this. Right, here's 0, here's pi, here's 2 pi. That's what the sine function looks like. And the cosine function, that one starts at 1 here, and then it decreases further, then it starts to increase and increases further. So the zeros here are at pi over 2 and 3 pi over 2. Well, that's the cosine here, the green one. Right, so what happens if you increase t from 0, right? What happens is the sine starts to increase first until it hits 1 at pi over 2, while the cosine decreases until it hits 0. So sine increases, sine is the x1 coordinate in this case. So that means we're increasing in that direction, and the x2 coordinate decreases simultaneously. So we're decreasing in this direction here. So basically, the curve starts to rotate in this way, right? That's the direction of movement of that curve here. Until we hit that point, and that corresponds to t equals pi over 2. Right now, the sine has reached a value of 1 and the cosine has reached a value of 0. Then the sine starts to decrease again, and the cosine starts to decrease into the negatives. So that means we're continuing our rotation this way until this here, that is the point pi. And you can probably guess how that continues. Now the sine goes into the negatives while the cosine starts going up again. Like, oops, sorry. Like this here. So the rotation continues. Here, that's the point 3 pi over 2. And finally, close that gap here. So now we are here. And now the cosine, so the x2 coordinate increases up to 1. And the sine is increasing from -1 to 0. So we're closing that circle here finally. And so this point, this point corresponds to 0 and also to 2 pi. Right, so the circle closes at 2 pi. So we're doing one full rotation of that circle, and we're doing it clockwise. And our starting point is here. And of course, again, there's a multitude of ways to parameterize that circle. The standard, the one that you usually use, looks like this: cosine t sine of t. And if you use that one, well, the result, of course, looks the same. You get a circle. The difference is the starting point. You would now start at 1, 0. So you would start here. So now this corresponds to t equals 0. And now what happens is cosine is the x coordinate, the x1 coordinate now. So x1 decreases while x2 increases. And that means you're moving in exactly the other direction. You're moving this way. Right? So this one is moving counterclockwise. And depending on what you want to do with your curve, of course, that distinction might matter. Even if you do a full circle, it might be important to know whether you're moving clockwise or counterclockwise, and where you're starting and where you're ending with your curve. Right? So here, that is the starting point. Whereas here, starting point is up here. And again, there's a multitude of other possible parameterizations of that same circle, with different directions, with different speeds, with different starting points. You could pretty much do whatever you want with that. So to give you an idea of how you could come up with different parameterizations of basically the same thing. Questions about this one?
Nope, no questions.
Wonderful. So let's add C. That's an easy last step here. So gamma 3, keep that one short. That has a parameter space from 0 to 6 pi. And gamma 3 of t is defined as sine t, cosine t, and t. Now that is a 3-dimensional curve, a curve in 3D space. The first part here, sine t, cosine t, we just saw that. You remember that was a circle moving like this one here, moving in clockwise direction and starting here. So of course, that's what we get here as well. The x1, x2 coordinate is just a circle moving in clockwise direction. And now we add a third coordinate, and that's the value of t itself. So the x3 coordinate, that increases from 0 to 6 pi linearly, basically, right? We're going from 0 to 6 pi, so that means that circle here, 0 to 2 pi would be one rotation, 4 pi would be the second, and now 6 pi, that means we're rotating 3 times around that circle. And at the same time, we're moving upwards. So that's kind of a helix, right? You have that circle, and you're rotating while you move upwards. So let's see if I can sketch that. Oops, somewhat appropriately. So basically x1, x2, x3. We're starting at 1, 0. So basically that looks a little like this. So we're rotating here around that axis like 3 times, right? So that's something like a helix. The suggested solutions will contain a better machine-generated plot. But you get the idea, hopefully. Questions about this one?
So far, I don't see any.
Wonderful. And let's move on to the next.
No, I have one. So here we have a radius of 1. How would the function look like if it has a different radius?
I'll answer that with B because I don't have the 3D component then. So if you have a function like that, a circle with a radius of 1, of course, you can easily make that a circle of different radius. Let's copy that. So if you want a constant different radius, then you could simply multiply by that radius and say, well, I'll define a function that has like 4 times this, right? And your starting point is not 0, 1, but instead it's 0, 4, and the radius will be 4 all the time, right? So you get a circle that's the same as it was before, just bigger. And of course, you can also vary the radius as you move along. For example, you could come up with something like gamma of t equals, let's say, t times sine of t, cosine of t, right? Basically, what you'd get there. And that means you're starting out again at the point 0, 1. So here, but now with the radius of 0, multiply that by 0. So you're moving there, right? So this is now your starting point. And what we said, the original circle is moving in this way here. So our movement stays the same, but at the same time that t increases, so we increase the radius as we move along. And that means what will happen is that we'll start to move. And at the same time, the radius will increase. That's not very good. At the same time, the radius will increase. And we'll end up with a radius of 2 pi, right? So t is 2 pi. Then we're back at this point, and then the radius will be 2 pi. So it's kind of a spiral movement, right? And of course, you can make all different kinds of more or less interesting spirals, and you can increase, decrease, vary the radius as you like as you move along that circle. That's where things start to get interesting.
Okay, and then I have one more. So should C start at x2 equals 1 and x1 equals 0?
Sorry.
Also, I'm guessing exercise C.
Did I start that at the wrong? I did. Yeah, let's relabel those.
Good solution.
Okay. Yeah, as I said, a better plot is contained in the suggested solutions.
Okay, that's it.
Okay, thanks a lot. So let's move on then to 11.3. So in 11.3, we are again given a curve, gamma, that is parameterized from 0 to 2 pi. With the codomain of R2. And it's given as gamma of t equals t minus the sine of t and 1 minus the cosine of t. Okay, and that curve is called the cycloid curve or cycloid curve. Basically, what that models is if you take a wheel, a circular wheel, and then roll that wheel and look at a certain point on the rim of that wheel, and that makes a movement, and this movement of that one point, that is modeled by this curve here. Very quick sketch, just to show you the basics. You don't really need to know this for this problem. So just to mention that, say you have this wheel here, round wheel, and you start to roll that wheel in this direction. So it moves this way along your axis, along your plane. And then you track a point. All right, so you track this point here. And that point will then start to rise as the wheel moves up to a certain point. That's what was a little high here, up to a certain point like this, and then it will start to decrease like this, and then it will rise again, and so on, right? So the movement of that point, that is modeled by this curve. Basically, what we have here is a curve that looks like this. So here's the point 2 pi, one full rotation of your wheel, here's 0. So this curve here, that's our gamma of t. Another question here is, we want to compute the length of that curve. And basically, that's just applying a formula that you should know, that we derived in the lecture. So the length of a certain curve gamma is given as the integral over the parameter space. So in this case, 0 to 2 pi over the norm of the derivative of gamma dt. So that's what we need to compute, right? We need the derivative of gamma, we need the norm of that, and then we need to compute that integral. All right, let's start with the derivative. Let's copy that formula here. So here's gamma, and then the derivative of gamma, gamma dot or gamma prime, that is given as 1 minus, well, the derivative of the sine is the cosine, so 1 minus cosine t. And in the second coordinate, derivative of 1 is 0, and then we have minus cosine t. The derivative of the cosine is the negative sign, so we have minus something negative. That's positive again, so we get the positive sine of t here. Right, so that's the derivative, the speed of that movement, if you want. And now we need the norm of that. So that means we have the square root of 1 minus cosine, 1 minus cosine t squared plus sine t squared. And let's try to simplify that. That is, the first term is 1 minus 2 cosine of t plus cosine squared of t, until we have sine squared of t. And as you've seen quite a few times now, cosine squared plus sine squared, that's 1. So we get 1 plus 1, that's 2, minus 2 cosine of t. Right, so that's the norm of that speed vector, of the tangential vector. So that's the value of the speed of that movement. And now we need to integrate along that to get the curve length. So our length, let's call it L gamma. That is the integral from 0 to 2 pi over the speed norm of gamma dot of t dt. So we have the integral from 0 to 2 pi over the square root of 2 minus 2 cosine of t dt. And the problem statement already gives us a hint on how we could solve that integral. One possible way of doing that is to use a trigonometric identity. And that identity that we use here is 1 minus the cosine of t is 2 times the sine of t over 2 squared. And as you can see here, basically that is 1 minus cosine of t times 2. And if we can reformulate that into a squared term, then we'll get rid of that square root here. So that's the whole idea of that trig identity. So integrating from 0 to 2. And we have the square root of 2 times sine of t over 2 squared. Right, dt. So now we can get rid of that square root. The square root of 2 times 2 is 2, obviously. And the square root of sine t over 2 squared is sine t over 2. And just to be sure, we need to take the absolute value here. And now, again, if we look at how that sine function works, let's take a quick sketch of that again. It looks like this, basically. Now, that is the sine of pi. And now what we have here is a sine of t over 2. And we're going from 0 to 2 pi. So basically, this argument here, t over 2, that is between 0 and pi, right? 2 pi over 2, that's pi. So we are entirely in this domain here. And that means the sign is non-negative anyway. So we can just get rid of that absolute value. Right, so that's the same thing as the integral from 0 to 2 pi to sine of t over 2 dt. And now we need to integrate that. We'll just keep the 2 here. And the integral of the sine of t over 2, well, obviously that needs to be something with a cosine. So let's see, cosine t over 2. The derivative of the cosine of t over 2 is the negative sign. So we need to add a minus to compensate for that. And then we would use chain rule. If we differentiate that, we would get the negative. So with the minus, we'd get the positive sine of t over 2 times 1 over 2. So we also need to multiply that by 2. So the integral is minus 2 cosine of t over 2. T from 0 to 2 pi. And then we're almost done. So this means what we have is 2 times. Now let's see, that's minus 2 times the cosine of 2 pi over 2, that's a pi. Minus 2, so that's plus 2 cosine of 0. And that means we get 2 times, well, the cosine of pi. Quick sketch of the cosine here again. So cosine of pi is a minus 1. So what we get here is minus 2 times minus 1, that's plus 2. And the cosine of 0 is 1, so we get plus 2 times 1. So what we have is 2 plus 2 times 2, and that's 2 times 4. So the final result is 8. Okay, so that's the length of that curve here. Questions?
There's one question. So why do you have to integrate over the absolute value?
Well, formally, what I do here is I have this squared expression. That's, of course, always non-negative. And then I'm taking the square root of that. That is always non-negative as well. So I have to make sure that this expression is non-negative. And to be sure of that, I use the absolute value. And then I'll argue why I don't actually need it. Yeah, but it could be the case. So if this expression inside of the square could become negative, then of course the square would get rid of that sign. So we would lose that. And we need to make sure that after the simplification, we also lost that sign, right? It's still positive or non-negative.
And then I have someone typing, but I don't see the question yet. I guess now we can actually. That was the last exercise, right?
That was the last exercise for today. Yes, right. So just a quick announcement, maybe. As you know, we are going to hold our exam using the TUM exam system once again. And for all those of you who have not yet had a chance to work with TUM exam, we'll do some kind of technical demo once again, where you get the chance to submit something just to test your equipment. Yeah, it's not mandatory to participate, and we won't correct that. It won't have any consequences on your final result and your final exam. It's just a way for you to experience TUM exam, the submission platform, and to see if your equipment actually works like you intend it to work. We'll do this next week. So probably we start next Monday after the central exercise session, and then you have like a day or two to do your submissions, or everybody who wants to participate gets a chance at doing so. I'll give you a few more details, and also for those who haven't seen the system, I'll give a quick introduction, a quick overview over that TUM exam submission system that we'll be using for the exam after next Monday's central exercise session. Yeah, just as a heads up, I'll have more details next Monday.
And it's very worth doing that, because it's sad when we supervise the exams and someone has, I don't know, their computer broke down, or
so there's not a lot where we can do if during the exam you realize that your scanner is really, really slow and you don't make the deadline. Bad luck. So please take the chance to test this before the actual exam.
Okay, and now I also have the last question. So could you please explain again why the integral gives us the length of the curve?
So basically, for a more detailed explanation, please have a look at the corresponding video. It's called curve length. From a mathematical point of view, just to give you the quick idea here, you have a curve, and basically what you do is you subdivide the parameter interval, and let's say subdivision yields these points here on the curve. And then instead of the curve, you use that subdivision to compute this polygon here. So you approximate the curve through a few lines. And of course, computing the length of these lines is easy. And then you just refine the partition. And this limit process yields the integral in the end. For a more physical explanation, maybe physics-based explanation, maybe you do remember from school that if you have a movement, something describing a movement, there is a relation between the function that describes the movement, the place of that movement, and the speed. And that relation was the derivative of the movement function yields the speed at a certain time. And basically that's the same idea here. So gamma, the curve gamma describes the movement. So the norm of gamma prime is the value of the speed. And that means you get the length of your movement by integrating over that speed. So basically that's what happens here physically. Right, again, for more details, please watch the video called curve length. There I try to explain that limit process in a bit more detail. Anything else?
Nope, I don't see anything else.
Okay, then I guess that's it for today. Thanks a lot for participating and for your questions, and thanks a lot to Eileen for moderating our chat today. As usual, if you have any more questions, you're welcome to attend our tutorial session on Thursday, 2 o'clock to 5 o'clock. We'll be ready to answer all of your questions. at least as far as I connected to this lecture here somehow. And also there's the lecture Q&A for the videos of this week that will happen Thursday morning. You can find all the data and the login data to these sessions on the Moodle page of the course. So that's it for today. Thanks, and I'll see you on Thursday.